When complex systems fail in the field, there is mayhem everywhere. Mechanical blames electrical, electrical blames firmware, firmware says we didn't make any update, and nobody knows what's going on. And I don't really blame anybody because it's really hard, especially in fields like robotics, power electronics. There are a lot of complex systems that are at interplay with each other, and it's hard for you to figure out what went wrong. So I have designed a system that I call the RLBT method, which can be used to solve all sorts of complex electromechanical failures in the field. So this system is reproduce, log, brainstorm, and test. So first of all, you have to reproduce the failure that happened in the field exactly. After that, you're going to log, you add a lot of additional instrumentation so that you can extract more parameters to be able to study deeply what happened in the field. Then you sit with the cross teams, the cross-departmental teams, and then you brainstorm the problems. And after that, when you have a strategy, you go and test it. And based on whatever test results you get, you can go back into the logging or the brainstorming session, and the cycle repeats until you found a solution. So let's start with the reproduce stage of this process. So it's very important that you first of all document in detail what happened in the field. This is also a problem in many teams because many of the times the people who are in the field are just going to say, oh, the system stopped working. Now nobody knows what's going on. Sometimes people don't even know how to describe what stopped working, which module was at play, and it's probably because they don't really know exactly what's going on in the system. The person who is a field engineer doesn't know enough about the system to tell you which module failed, right? So first of all, we have to have a process so that we can document in detail what happened in the field. Now, once you have that information, you should be able to go ahead and reproduce that in similar conditions at your home turf in the company. So I understand that this is not possible in all scenarios, but wherever possible, we have to try to make that happen. So if your system had certain ambient temperature, if your system was under certain operating load, if it was using certain operating system, then you have to try to make sure that all of the same things are available here as well. And sometimes it might happen that you're not able to reproduce a problem. Maybe you can't reproduce a problem by the same operation because somebody tells you, we were operating the system in the field and all of a sudden this failure occurred. Now, there's no real definition for all of a sudden, but you can define and describe what kind of failure happened in the situation, and then you have to figure out how you can induce that particular failure. So as an example, in one particular case where I was testing an embedded system that's used for controlling robots, I used to have this error where all of a sudden we would have certain cases where the system would suddenly glitch and it wasn't able to do the actuation that it was supposed to do. It was trying to operate a valve in that situation. And so lo and behold, the way we actually were able to induce that error was to suddenly yank the USB cable out of the system because it was operating and handling multiple different peripherals at the same time, and doing that helped us induce that particular failure. But this is not a failure that I had thought about because the way it represented or manifested itself when I was testing was different from the way I had to induce and produce it. But that induction of failure helped us understand the mechanism of failure, because of which we were able to go and fix it later on. Now, the second step in the process is to, once you've identified, once you can reproduce or duplicate the process, we have to then go ahead and log this particular system, add logging variables, or add some sort of mechanism to be able to extract additional information about the system. Now, this could mean different things for different domains. As an example, if you're thinking about a mechanical system and you want to add additional information, then the way you would do that is maybe by taking some pictures, maybe because if you're trying to see, well, I think that this particular area in the gear or this particular portion of the shaft usually ends up getting certain scratches, right? So I might want to take some pictures and observe that again after running the robot or some system for 100 cycles. That's a very crude method. You can also add additional sensors. You might be able to look at sensors like temperature sensors, or depending on what kind of instrument, what kind of system you have, you might want to have some liquid level sensors, oil level sensors, and so on. So this again is very domain specific. It depends on the problem that you're looking at. For electrical systems, you might again want to add certain variety of sensors. You might want to add oscilloscopes, multimeters, And these kind of systems will be used while you're running the test, right? So the idea is that when you're reproducing the problem, you have successfully done that. Now you're going to redo that while adding additional logging mechanisms. And then finally, my personal favorite is via software because it's the easiest. So if your system is already getting a lot of data from sensors, but it's not actually logging that information to memory, then it's very useful for you to add a lot of verbosity to those systems when you go into this sort of a debugging situation. And that's because you don't want to have these at all times, because obviously if you log that information, every float or double variable is going to occupy 4 or 8 bytes of memory. And when you keep doing that every 10 milliseconds, 5 milliseconds, 100 milliseconds, whatever your loop period is, it's going to quickly eat up your memory. So this is something that makes sense only when you're trying to debug. So during debugging, you should add additional logging information and then look at them later on. But for each of these things, it's important for you to understand that you don't want to do anything which makes it difficult for you to reproduce the initial situation, right? If I know that my system has, for embedded systems, for example, in embedded systems, you typically have a loop period after which the system repeats its cycle of instructions. So if your logging is actually causing it to overflow that loop period, then you fundamentally change the way your system behaves. You can think about it in terms of quantum mechanics, right? The act of measurement is changing the way your system initially was. So on a macroscopic level, this usually does not happen, but you have to be careful that any sort of instrumentation that you've added does not change the fundamental behavior of your system. So be careful with that. But once you have that information, now you can do a variety of things. So as an example, I remember there's one time we were trying to debug something with the stepper motor of a robot, and we couldn't figure out because it seemed like the motor stalled at certain times. It wasn't clear to us why in certain situations this behavior manifested but not in others. So I had to go ahead and add a variety of variables, and to do that I basically went through the datasheet of the motor, looked at all the ways in which I could query those specific parameters, and then I started logging those variables at whatever frequency I could talk to the motor at. And once I had that information, not only did I figure out a lot of problems in the way this situation was manifesting, but also other issues in our system which we didn't know about before. And this is actually one thing that I think all teams should learn, because what happens usually is that software engineers will be very good at writing code in C or C++, and they will write code thinking about algorithms or logic, but they don't usually look at how it manifests on hardware, right? So it's very important that once you execute this system, once you've thought about the logic, you actually make sure by looking at the data that it looks fine. Like when you look at the plots, they should make sense to you. This is where I feel like not only during debugging, but also during development, it's important to make sure that people of different teams are sitting together and they are speaking a language that everybody can understand. And I'll talk a little bit more about this in the next step. But one more example I wanted to give where there was cross-team collaboration is when we got new wheels for robots that we were working on, and we wanted to see what effect these wheels have on the system. Does it improve the overall efficacy or not? Are we able to settle faster? Do we think that the overall system performance is decent or not? So really what we wanted to check was, well, these new wheels that have been added to the system, it's a new material, right? According to mechanical team, this was going to give you more benefits, right? So they had done their analysis, they had done their simulations, they'd done some practical testing, and they felt like this should do better. But the only way for you to know whether it actually did these things or not is to look at what the motor currents were. How were the various sensors in the system reporting the performance with these wheels? And the way to do that was to talk to the software guys or the controls guys to make sure that we have real-time logging information for this particular performance, for the performance of the motors or sensors or other actuators when you have these wheels, and do a comparison between these two in a statistically significant sense, right? So you compare enough number of cycles on enough number of robots to be able to come to a conclusion that this thing is actually better. So again, these things, when you add more logging for across domains, electrical, mechanical, software, you'll definitely be able to visualize your system better. And then the third step is brainstorming. Now, this is a very important thing. When you have a complex system failure, which involves multiple domains, usually what happens is people end up blaming each other. And what I've observed is that regardless of the industry, the person or the team or the company that gets blamed is the one that's closest to the user or the most downstream. So for example, if you think about a robotics company, then you will have a lot of like a planning layer at the top, which is like the software architecture. And then after that, you will have a motion planning layer, then you'll have a motion controller layer. And of course, there could be further subdivisions. But if the robot fails and you think that the motors are working fine, then everybody's going to come and blame the motion controller and be like, well, what happened? What changed in the motion controller? Why is it not working? And usually, not always. In my experience, it was always something else in the system. But again, we can't generalize this. But in the same sense, if you look at a solar system, for example, you will see that there's a solar panel. After the panel, you'll have a multi-point power tracking MPPT system, and then after that, you would have some other components, like you will have a battery, you'll have an inverter, and then you might have some other different systems depending on what kind of an overall setup you've made. And again, if something fails, people are going to say that it's a fault of the solar inverter, even if there's something wrong with the battery, there's something wrong with the panel, because the users cannot interact with a panel. They can only interact with an inverter. The inverter is the one that's giving them that information. So obviously, that's the person they're going to blame. But I think to the fullest possible extent that we can, we should try to make sure that we don't blame teams within the same company. And we come to the table knowing that we are trying to solve a complex problem together. So as far as the logging step, the brainstorming step is concerned, now that you have all the people in the team and you're not blaming anybody, we want to make sure that everybody speaks the same language, because the language that an electrical engineer speaks is not the one that a mechanical engineer can speak. If I, as a software engineer, decide to show code to the electrical guy, maybe they won't understand anything about the logic that I've implemented. And likewise, if schematics are shown to a mechanical designer, they might not have any idea of what's going on in the system. And it's not just about the fact that they won't have any idea, it's just that they can't contribute effectively to that discussion. And that's not something you want when you're trying to solve a problem. You want every brain contributing, trying to solve that problem. So what you need to do in such situations is that you have to speak a language that everybody can understand. So I think that the way I like to solve these problems is that when it comes to code, you have to make sure that there's a flowchart. Actually, there should be a flowchart for everything. For your electrical schematic, if you can boil it down into a simple flowchart that people can understand, then they can have a discussion with you, even if they don't understand how the individual components work. If I can say that, hey, this subsystem, when you send a signal, it's supposed to respond in this fashion, and this will trigger this subsystem, which in turn will be picked up by the firmware, and that's going to actuate something, which is then going to cause the motion of a motor or a valve or something, and therefore the mechanical motion will be induced. Then a lot of people can come and talk to you about how these things are orchestrated. So that's about flowchart. But then when you're specifically trying to debug a problem, the favorite tool of mine is cause and effect diagram, or it's also called a fishbone diagram. So people think about, there's an effect, we saw a failure, what are the potential causes? And then you start creating branches for each of those, and then you think about, okay, well, this could be a branch for mechanical reasons, for electrical reasons, for this particular type of software module, and so on. And then for each of those, you try to cross out why that could not possibly be. And if it is actually a reason, then you go ahead and investigate that. So I think speaking that common language helps everybody. And then the most important thing, which I think if in any dynamical system, is that you should be able to look at real-time plots. So if I can look at the current measurement or the position or the velocity or whatever dynamic variable of my parameter is being logged, then everybody in the team can see how things vary, right? So one example I can give of this is there was one time I was working on a robot where we started having these issues where the robot was moving vertically in a structure, and every now and then it would just fail in the middle. And we couldn't understand what was going on. We checked the software. It didn't make any sense that this failure was occurring. All the instructions were being followed to the T. There was nothing wrong with the motor. The electrical team looked at it, and we did individual tests on the motor. The mechanical team could see that there were certain wear and tear on the shafts, but it wasn't obvious to anybody what was going on. And so what I started doing was, without knowing exactly what I could see at the end of the tunnel, I just started logging a lot of variables, and then I started plotting them together. And without going into a lot of detail, what I found was there was some correlation between different data points, which was non-obvious. And by investigating that, we then got some sort of an error. And with certain manipulations, we were eventually able to reproduce, right? So this enabled us to get to the reproduction part. And then the whole process followed, and we were able to solve the problem. And then another example that I would like to give of this is that we had an instance where, the mechanical team observed that on a specific robot, there was a lot of wheel failure. Like there was a lot of the rubber was chipping off, there was mechanical damage, and it was not obvious what was going on. And then again, once we started looking at the data, we looked at the plots, right? When we looked at these plots, and that was a language that electrical, mechanical, software, all engineers could understand, we were able to see, okay, so the the motor current goes up, and that's because this portion is getting stuck, and that's because there was a mechanical misalignment. And then we were able to come to the conclusion that this problem is a mechanical source, and we can fix it. And then final stage after this is that you got to go and test the system. And in this process, again, you have to be very careful that the same test conditions that you use for reproducing the error are the ones that you use here, and you're objectively able to show that the error has gone away. And it's very important to be careful that you can't just do 1 or 2 tests or say, oh, I tried this, and then the error didn't occur again, right? You have to be able to stress test the system. You have to be able to test it on a variety of systems, and you have to test it a statistically significant number of times before you can come to the conclusion that this system has genuinely been fixed. So that's it. That's the RLBT method, which I've used for fixing various problems for complex electromechanical systems. If you or your team has used other systems, let me know. I would love to hear other ideas from all of you guys. Thank you.